That's enough. After the withdrawal date and during break,
Yeah.
a bunch of people
Yes.
That's how I got into everything. Like everything when I tried to register was fully booked. Because now I might not be able to graduate. And me through and and then I checked online and like 3 slots it opened up.
No, the thing is, registration for this semester was over the summer, and all throughout the summer, no spots for being 335 or.
What are you talking about? No,
They were
last spring.
Oh yeah, last
It's
spring.
always the spring.
Yes, but you can carry on registration all the way through the summer,
Yeah, no,
as long as
that's-
it was before 2 weeks before class.
That's what I did with prof.
And that's exactly what I had to do for AE.
So instead of getting to E, you did AE301, which is everything.
It's such a fun class.
Is it?
Everything is so much fun. Everything. Everything you talk about. Okay, I'll say this. If you try, you will pass. If you do everything he says, you'll get a B practical guarantee. And since his assignments are open-ended, if you give more than what he asks for, he's willing to give you a 95 to 100.
Oh, yeah.
Yeah.
I've never had it.
We'll see how that goes, though. Including last 8 classes.
Sigma gave it now? Yes. Yeah. Were you invited? I'd say it's worth it. It's something you can slap on your resume. Like, if you get invited to the better college high, like, those are the 2 So, like, yeah, it's worth it. The application process took me like a day. You can't talk about it.
Oh, what?
Do you have any questions?
I can't talk about it.
I hope you
I can't talk about it. I cannot, that would be, I cannot talk about it.
I hope you are enjoying it.
Giving them.
Yes.
Oh, I would be preferred if you did like business cap. Where about
Any question about homework B2?
I'm above average.
I propose.
Yeah, yes, yeah, that's just
Well, I'm
it.
just happy if I am. He's saying I'm still struggling to meet them.
For me, like, my other class, I can get a 4. I can get a 4.
Somebody.
Okay.
Looks like we got 2 people online today. How you doing? Can you hear me?
Yep.
Okay. So I'm gonna mute for a moment, but if you have a question, I'll mute microphone, okay? Alright.
I mean, honestly, on top
Okay, let's take in-class attendance video. Don't worry about the paper anymore. I know you. Don't worry.
I talked to a lot of employees and they said, I'll not be able to do 35 per year, but they said, they'll have no problem sticking with the grades.
Hold on.
That's what I've heard from a lot of employees. My, and he said there was one where, I mean, he obviously hired my kids, and maybe I'm out of 3
That's incredible.
and you're two on.
Alright, good. So, as you know, you have homework which is due coming up Friday night. So, if you have any question, okay. One of the problems is probably impossible to do. It's just to go over. What was the question, Michael? You brought
It
in.
was B2C.
B2C?
Yeah.
No, that's easy.
Oh,
It's not
and
this
then it's
one.
B1.
Oh, it must be this one.
Yeah, I'm.
This is probably something that if you really understand what is school function, kind of problem, but otherwise it's probably near impossible to solve this. So I'm gonna show you my solution. I'm not gonna go over it. I just show you. And then since it's videotaped, that means I release my solution. That's what it is.
Can you also post it?
I'm not gonna post it, I'm just show you. Because it's your work, you know, I'm not gonna, well, this is your work, But I just wanted to show you how I did it. B2 to B, okay? This is actually, I think it's quite important homework, is not this one. What's going on? B2 to B.
Are you allowed to take pictures?
This is videotaped, okay?
Oh.
Okay.
Okay, no problem. Okay, so you can take pictures, but it's a videotape, all right? Okay. So let's just understand properly, what am I asking? I'm asking you to find, okay, so what is the stream function of this field? That's the first thing you have to find out. Because once you find out what is the stream function, the rest is easy. Okay, because stream function is solution of a process equation that actually governs the flow field. So the entire purpose of this unit B3, that's what we're going to begin today, is going to do some, solution of the process equation using a technique called superposition of elementary flow solutions. That's what we're going to take a look at. So this program actually sets the very basic standard and purpose. And why are you doing for what you're doing? Do you really understand kind of thing? So velocity field is given, okay? Velocity field is given. So what is the original velocity field? Is it given Cartesian? I think so, yeah. So Cartesian velocity field is given. So first step is you're going to express,
Polar.
So velocity is given in polar coordinate. Oh, that's right.
Yeah.
Okay. So velocity is given in polar coordinate. So you're going to, first of all, polar coordinate to Cartesian coordinate system. You're going to try to express your velocity field in terms of x and y. Cartesian flow field. You know, the velocity p is equal to ui plus bj, right? Then this is u, velocity in x direction component, minus cy. C is a constant. Okay? Velocity b is a cx. So now you know the velocity field is given in Cartesian coordinate system, which is basically, hey, I found the velocity given is ui plus bj. Listen, you can copy it out if you want to. If you have no clue as you copy, you're going to screw up anything big time. So I don't care. So important thing is, do you really understand the concept or not? Because that's going to be tested. Okay? So you can copy, of course. I mean, this is videotape, okay? I'm videotaping right now. I cannot hide anything. This is my solution. So this is what you're trying to find. And then, of course, u is equal to what? Negative cy. B is equal to Cx, right? Right? Okay, so now you're going to start from xy plane equation of streamline. Plug that in, then you ended up having this kind of function, mathematical function. Right?
C is just arbitrary constant.
That's right, C is constant.
Okay,
C could be anything, yeah, that's right. So you can integrate this, right? You can integrate this. So this is your attempt to integrate, and then integrate and combine some of the constants. In other words, you're going to redefine constant C with combining other constant, and then, hey, this is what I got. What is this? Equation circle. And then that means this is my stream function.
Okay.
Oh, so the rest is easy, right? Suppose if you plug in x, y equal to 0 and 2, this is going to define a particular streamline, the equation of streamline that actually goes through x, y equal to 0 and 2. That actually corresponds to the constant being 4. So this is the equation psi equal to 4, right? And then what is the equation of streamline that actually goes through x, y equal to 5 and 0? That actually gives you constant, becomes 25. That means, hey, this is the equation of streamline psi equal to 25.
Do you want us to draw the circle?
Yes.
Because this is the equation circle. Okay. So you can draw any number of streamline by setting lots of different constant values, right?
Yes.
That's what you're going to do in project 2A, 2B. Do you understand? Go ahead, question.
Yeah, I was just going to ask because doesn't the aerodynamics of the particle doesn't go in a like specifically circular motion, doesn't it? Like
It does. It's called vortex.
Okay.
Yeah, it's a vortex type of flow. We've seen like a wingtip vortices, this kind of flow here. Yeah, we have that. So this is actually one of those physical phenomena actually representing vortex flow. Right.
So do we define a constant for psi and find an equation, or do we find a point that?
You have to
passes
find
through?
out first of all psi.
Yeah,
Because this is the governing function.
Yeah.
Now the rest is easy. If you set psi equal to different value of constants, that actually produce each one of those, basically equation of streamline.
yeah, no, my question is just generally, are we setting psi to different values, or are we telling at different points what is psi? Or
You can do either way.
either way?
In
Okay.
other words, this is the line actually connecting psi value equal to 25 locations. This is a contour line. So along this path, psi is always 25.
Oh, okay,
This is contour line.
got it.
Okay, so this is along this line, psi is all 4. Suppose if you say psi equal to 10, it's probably this kind of line. Psi equal to this kind of line.
Got it.
Those are contour lines. Go ahead.
So for the one that says in polar coordinate system, that's another way of doing it.
What are you asking?
For C,
C. What is C? Ah, C. C is what? What is
in polar
question C?
coordinate system. But
What is the question C, by the way? Do you remember?
it doesn't say.
it's asking you to graph.
Yeah. it's
Eh?
just on the graph.
C. Sketch,
Right?
It's just streamline.
sketch these two streamlines.
So is it just,
It's just the graph, isn't it?
Yeah.
so
that's
what's
it.
this
What's
polar
this?
coordinate stuff?
In polar coordinate system, velocity is given.
Yeah.
Ah, okay. So what is the circulation for this flow field? Isn't that? Am I asking you that? No.
No,
I would like
What
to
the
know.
how'd
hell?
that get there?
Maybe this is a carryover from last semester's problem. I modified it, but I forgot to modify the solution. So suppose if you have access to the last semester solution and copy it out, then you get caught in PA41. Be careful. I make mistakes. I'm human. So if you have access to last semester's solution, be careful before you copy it out without looking at the problems. So forget about that. Good point, Robert. Forget about all this. This is not even being asked this semester. So last semester, apparently, I asked you, okay, what is this? What is the vorticity of this flow field? That was problem C. Yeah. So I modified it, but I forgot to modify my solution. Sorry. Oops. Oops. Sorry. Oops. I shouldn't have said that because this could be a trap. I always do traps with my homework assignment because I create my own homework assignment. I can easily create a little bit of change and variation of it, try to see if someone's copying from last semester without knowing what you're doing.
Does that
So
explain
don't
why?
play game with me. Anyways,
Does that explain
I
why?
appreciate your question, Robert.
Yeah, because like
Really?
the last solution
That's the solution. Which one?
from unit A,
Which one?
the way you were
So
converting.
again, which one?
Okay, okay. I would
Let's
say,
take a look at which one. That's the solution of unit A. Which one? Which,
it's for
unit A. Where? Which one?
I would say,
You would say
let's say A1.
A1. One.
A1 of to the,
A1 to B.
is that involved conversion?
This is A1 to B.
There's just one part where like
Yeah.
you're converting, but the
Combining-
fractions aren't flipped correctly.
Which one?
I don't know if it's in that one or.
Yeah.
I don't know, I studied it a long time ago.
I still don't know what you're asking. What are you asking?
So, is that the trap you're talking about? Where,
I can always create any trap. In other words, I pretend like, hey, this is the same problem, but I can change a little bit from last semester. So it looks like the same problem, but it's not.
yeah.
So if you believe, hey, this is the same problem from last semester, I have a copy of last semester's solution to copy down without knowing this is a
Oh, I
different
see.
problem. It's easy. It's easy to pinpoint, hey, do you copy from last semester's solution?
Okay,
That's PDA41 straight out.
okay.
You will be sent straight to hell. I can easily do that because I create all the problems, I create all the solutions, I know everything.
Would you send us there?
I am the creator of this whole system.
Okay,
of-
yeah, it's officially done.
I know everything. So you cannot play games. So anyways, thank you for your question, Robert. So please be specific. I can walk you through that if you tell me which one you're talking about. Anyways, any other questions? So I showed you what I did. So forget about this. Let's see. Let's see the sketch, right? This is the sketch. So this is essentially contour plot of the stream function psi of the flow field you define. That's exactly what you're going to do in project phase 2A and B. Okay. So understanding concept is quite important. So this is kind of problem you can actually solve it not knowing what you're doing. That is very dangerous. Okay. It's easy because this is equation circle and all that, but why are you doing it and what is the purpose? The purpose is trying to define the stream function that actually governs this flow field. Okay. That's the whole point of doing unit B3. Any question of homework of unit B2?
I have a question on the homework, but it's not on the project.
Yeah,
So,
project, okay.
yeah,
Oh, project, huh? Project 2A, yeah?
yeah.
It's a fun project.
It looks fun. I like the pretty graphs.
Yeah,
I want to be able to make those. It's just not happening yet.
Shapes and colors.
yeah. It will take some time to get it. In other words, yeah, okay, so project 2B, not the 2A. Project 2A, you are going to actually do this kind of plot. So this is the things that hopefully I'm going to cover today or next class.
Okay.
This is a superposition uniform flow and source, which is going to create the flow over like a leading edge of airflow.
Okay.
Okay, and then the other one is, of course, flow over circular cylinder with a different value of stream function equations. In other words, this one represents psi equal to 0. This is one of those equations of streamlines. Psi equal to 0.4. This is positive value, this is negative value. You can draw any number of lines corresponding to each different value of psi. This is contour plot. And each one of them represent equation of streamline. This is psi equal to 0 line. This is psi equal to 0.4 line. Psi equal to 0.8 line. That's what you saw in the homework assignment, right? Okay, essentially it's the same thing. Once you know what is psi of this flow field, the rest is you're going to draw contour lines to represent flow field. That is potential flow analysis. Okay, so I guess it's a great idea to start early. And then I hope as I'm moving on in Unit B3, lots of those questions will be answered, naturally speaking, okay, before you start actually finishing up your project. Don't worry too much about it. Code itself is, I don't know, 50 lines. That's a piece of cake, if you know it. Okay. How much time do I need to spend to create the code like this? 10 minutes. Okay.
Thankfully, we are not you.
That means that, well, that's the value, skill of engineers. Okay. Understanding the concept versus I have no clue, but I'm trying to pass this class. It's a big difference. One is engineering, one is BS. Okay. So don't worry too much about it. As you kind of get more understanding, it's going to be easy. Code itself is a piece of cake. I actually have a code here, but I think it's too early to show you. I coded everything in TypeScript, yeah. And I'm going to show it. I'm going to share it with you, okay? Well, I don't have to share because this is something you have to produce anyways. I don't have to share my code anyways.
So it looks similar to that, then it probably works.
Well, it looks exactly the same. It should be. Not the same. Exactly the same.
Yeah.
Okay. All right. So let me get in. Let's get in and take a look at Unit B3. It's going to be exciting. Actual application potential flow analysis. Okay. So step-by-step mathematical process to analyze flow field. Okay. So first of all, before we even begin, what are we going to do? This is all about theory of aerodynamics. That means you're going to step right into here. Theory of aerodynamics. Pure theory. What do you mean? 100% mass. 100% mass is is the reason why you can actually use the software like X5, Xfoil, X5. This is essentially 100% mathematical analysis potential flow field. So before we even begin, we need to understand what is the simplification assumptions already built in. This is simplification assumptions. Simplified equations based on those conditions. So this is steady state flow. Viscosity is completely ignored. Body force is zero. That means gravity is even not considered. Incompressible means density constant everywhere. Irrotational is quite important mathematical simplification. In other words, vorticity del cross B, if you compute within the flow field, it's always zero. Irrotational flow field. And then you can say lots of interesting things. You can express equation similar to Bernoulli, but not quite Bernoulli, something called ideal flow equation, right? Like P plus 1/2 rho V squared is constant everywhere in this flow field, right? And then once you know the velocity, you can determine pressure coefficient, Cp is equal to 1 minus V over V infinity squared. This is called pressure velocity coupling. Okay? So those are the equations you can, of course, pick it up and use it. Okay? And then this is called ideal flow. Ideal flow is not equal to real flow. So ideal flow behaves kind of weird because you're completely ignoring viscosity and density is constant everywhere. It's not going to separate over the surface. So ideal flow field, even though real flow field, of course, your intuition says if you pitch up your airplane like this, it's not going to fly, obviously. Okay, what happens?
Stall.
Stall.
Separation.
Of course, this kind of thing happens, right? This is real flow. But if you do the same thing for ideal flow field, it behaves differently. It behaves somehow like this, maybe. Okay? And then you go like, oh, wait a minute. I don't think so. So, ideal. So you have to be very careful. When you receive an ideal flow solution, you're not going to take it as it is. Okay, well, I'm going to apply this result into the real airplane analysis, and you can't do that. Of course, this is ideal flow. So you have to always think back, and then what is being ignored? Can I put back on things that we are ignoring into our model? Yes, we can do that. That's the step-by-step process. In other words, this is the baseline solution based on ideal flow solver, but we've been ignoring viscosity. Okay, so let's turn on the viscosity model and then add on to this ideal flow solution that is more realistic solution available for you, including viscous flow analysis. Add it onto it. Okay, can software do such a thing? Yes, you can. This is actually ideal flow. And then what's Mach number? Anybody?
That's 7.3.
We don't care Mach number. What is Mach number? I don't know. It's ideal flow. But we know density never change. So realistically speaking, suppose if you're talking about Mach number now is 0.7, density is not going to be constant. You have to correct, modify the values you calculated based on ideal flow analysis. That's called Prandtl-Brouwer correction. We don't cover that. Software can do that, of course. Go ahead.
So is the reason there's no turbulent flow because it's irrotational in the ideal model?
Turbulence. What is turbulence? Where does the turbulence comes from?
Flow separation.
Flow separation comes from where? What is the physics behind flow separation? What causes flow separation?
No constant.
Viscosity. Viscosity is completely ignored. There's no such a thing called boundary layer formed up for ideal flow. If the boundary layer doesn't exist, we cannot even say is it turbulent or laminar flow, because that's all about boundary layer discussion you're talking about. Flow separation is also boundary layer separation, but there's no boundary layer. That means implicit means over the surface of this body, flow is hitting here, creating stagnation point, then slide over the surface, and then another stagnation point, flow away. That's ideal flow. over the surface of the body, flow slide over. Real flow field, you have a boundary layer, velocity 0 on the surface. There's no such a thing. But you can add on those kind of model later to make it more realistic solution, okay? So now we are talking about pure theory means that this is 100% mass. In order to have 100% mass, you have to simplify it. Remove all of those variables, otherwise you have to deal with second order nonlinear partial differential equation. Have you seen that kind of stuff? Del cross B. Do you want to do that? You can do that, but you cannot solve it by hand. Okay? You can only simulate using computer simulation, which is not solution at all. Okay? So that's what we are doing. So we are going to do hand mathematics. As long as we cannot do hand mathematics, it's not called the theory of aerodynamics, but we have to start from there. It's always easy to make things more complicated. It's easy to start with, okay, I'm going to solve this three-dimensional airplane, fully turbulent, highly unsteady, high speed. Let's just solve it using CFD. People say that kind of stuff. Do you think you can do it within an year of your senior design? I can guarantee there's no way. It's almost like you're saying, I need a PhD. By the way, I need it by next weekend. Same thing, you're saying that. There's no idea there. I mean, what do you think? It's insult almost. I spent 10 years. I mean, practically speaking, I became blind because I read too many papers. Then I barely got PhD. Okay? Why is that? Because it's way too many things involved. Too many variables. And humanly speaking, you can never understand such a thing every detail. But we try to understand because we apply simplification equations. Okay? So this is the background, always. And then what we can get is ideal flow solution. This is not the real flow, but great thing is this is 100% pure mathematical solution. Okay? So let's begin. So this is a step-by-step process you're going to be involved. We are going to start with someone's already available elementary flow solutions of Laplace's equation. Elementary solutions exist for Laplace's equation. There are so many elementary solutions, and then some of them are applicable directly to the flow field analysis. That's called elementary flow field solutions of Laplace's equation. I'm going to introduce you 4 different elementary solutions, okay? Now, once you are given those elementary flow solutions, you are going to combine those. Okay, I can add uniform flow and source. That's going to create kind of flow field. This is kind of similar to flow over the leading edge of infinite body kind of thing. But I need a trailing edge too. Okay, let's superimpose source and sink and uniform flow. That is going to create a flow over like a body with leading edge, trailing edge both. Well, we want to do like an angle of attack. Well, okay, well, it's just a shift it. This is source, this is sink, uniform flow. Okay, well, this is some kind of body, leading edge, trailing edge, pitched up. But I want to have a NACA 2415. Okay, now what? So now we are moving to panel method. Okay, we are going to pick up small tiny panels, represent actual shape of your design. Then superimpose against uniform flow. Then set the surface equal to the stagnation streamline. So we are going to cover one step at a time. Okay. So elementary solutions, we are going to introduce first of all uniform flow. Uniform flow is something like this. Typically from left to right, magnitude b infinity in x direction, positive, uniform flow. Okay. The other thing is source and sink flow. This is quite interestingly straight violation of continuity. Divergence becomes either positive or negative, which is mass can be created or mass can be destroyed like a black hole. There's no such a thing in physical flow field, but this is source and sink flow. This is one of those solutions of the Laplace's equation. We actually pick it up and use it for a flow field simulation. So let's say single point. Flow is all of a sudden starts to happen from nothingness with a magnitude lambda. Magnitude lambda is a volume flow rate or mass flow rate, either way. Mass flow rate if it's compressible flow, volume flow rate if it's incompressible flow. This is called source. Like I said, this is a straight violation of continuity. So you cannot really use this single point as a realistically mathematical solution for real physical flow field. This is called mathematical singularity point. Be careful. Mathematical singularity point is something you can never pick it up as a physical solution of this whole thing. Okay. Sink is like a small tiny black hole. Right here, all the flow is sucked right in and disappear. This is called sink. Magnitude is negative lambda. Source and sink flow field. This is one of those elementary solutions of Laplace's equation. We can actually pick it up and use it to simulate the flow field. Okay. The other one, elementary solutions, doublet. Question, go ahead.
Yeah. What's that symbol that next to your source?
Lambda. Capital. Capital.
Yeah.
Capital Greek.
So draw delta minus minus the third bar on the bottom.
Negative.
That's
Negative
lambda.
lambda. Okay. Lambda. Lambda.
Yeah, that looks like an omega.
Yeah, I was gonna
That
say.
looks very much like an omega.
Omega
It's
is
like
this.
Yeah.
This is omega.
Yeah, if you write it
This is
quickly,
lambda.
if you write it quickly enough, no one's gonna tell.
Or maybe lambda must
That's
be
lambda.
like,
No, stop that third bar, and there you go.
stop that box.
Stop completing the triangle.
Just a triangle?
It's up down. That's it.
Down.
Upside down B.
Okay, if the Greek guy says so, how far?
Do not complete the triangle. There, lambda.
Okay. Lambda. This is omega. It's like octopus shit. Okay, anyway. Lambda.
So what did you
Doublet.
learn there today?
Doublet is a combination of sink and source pair at the single point with the same magnitude. So if those two combine into the single spot, it is going to create the flow field just like this, okay? Source create the flow and sink suck right in. This kind of flow field. It's weird, isn't it? So source create the flow, sink suck back right in. This is called the doublet. Source and sink pair at the single location. This is already superposition of those two at the single spot. It's called doublet. Doublet's magnitude is kappa. Kappa. Lowercase Greek again. Not the K. Okay, this is kappa. Kappa. Not the K. These are lambdas. Okay, so this is doublet. Okay. The number 4 elementary flow solution is called vortex. You've seen it already. So vortex is going to be a flow field which is essentially creating the streamlines of concentric circles around a single point. So this is called point vortex. Now this is again irrotational vortex. That means the vorticity is 0. However, there's a circulation. That's the magnitude of vortex. It's a circulation. Okay, magnitude of vortex is a circulation. Gamma. This is gamma. Uppercase gamma. Okay. So those are the 4 different types of elementary flow solutions. Now we are going to start from. Then we can superimpose those things to create flow field. Go ahead. Question.
If the vortex flow is going the other way, is it negative?
It's negative. Yeah, that's right. Magnitude. Go ahead.
Is that the same for a doublet? Does it have to go
Yeah, that's right.
front
Okay.
to back?
So doublet could be positive or negative, direction-wise. Yeah, that's important. So you could have a negative doublet, positive doublet. It's going to be left-hand side is source or left-hand side is sink. Either way. Go ahead.
For that example that you showed us in class for the homework, V2, is that stream function graphing a vortex then?
That's a vortex, yes.
Okay.
That's correct. Okay.
If you have a doublet where half of it's a sink and half of it's a source,
Uh-huh.
do they have to be of equal magnitude? Where
It's a negative magnitude.
Oh,
That's right. Direction-wise, yeah. It's going to be flip-flop. So negative sign comes up.
So what if they're not the same magnitude?
Like you have one that's.
If it's not same, if it's not same magnitude, it's gonna create weird flow field, which is not doublet. It's not called doublet, but some kind of flow field. We can simulate that.
It's not
I have
a
a
doublet.
software. Software means this software, isn't it? So I'm gonna run ideal flow machine. So this ideal flow machine actually simulate any of those. So I'm gonna probably give you the website link for this toy. This is toy, right? You know, you can actually simulate. Okay, so what the heck is doublet of a strength of like I don't know, 20, and then put it in here. Then you can draw a streamline. So what is doublet, anyways? So, oh, this is doublet kind of thing. You see that? Ah, this. This is a doublet. Okay, as you can see. So this is doublet flow field. You can do any number of streamline. Like I said, this is the streamline is the number of same value of psi in the data field. You're gonna do the same thing as contour plot.
It's always symmetrical.
This is a symmetric. So suppose if you superimpose source and sink with different magnitudes, it's probably not gonna be symmetric.
No.
Yeah. Okay.
Are you allowed to rotate the doublet?
No,
Does
you
that do
can't.
anything?
I don't think so. Ah, you can. I don't know. Rotate means what? Flow field. Well, yeah, you can do that. In other
So
words,
like an 8, it would be like an infinity.
could be. I'm not sure. So that means you're going to superimpose in y direction. So source and sink pair is going to be staggered up and down. That could be. Okay. Anyways, you can do lots of things if you are curious about. Let's just use this toy and then find out. You can superimpose anything. Okay. So like I said, so those are the 4 different kind of elementary flow solutions. So in this class, I'm going to actually start doing uniform flow plus source. This is the superposition of 2 solutions, source flow and then superimposed against uniform flow. This is going to create the flow field around semi-infinite body. It is going to simulate the flow of like a leading edge of a semi-infinite body. Okay. Uniform flow and source and sink pair, it is going to create the flow over some kind of body. If you have the same magnitude of source and sink, it is going to create a symmetric body. Okay. So let's go flow around a oval. The other one is uniform flow plus doublet. This is something you're going to work on. So this is a project 2A. This is going to create flow around circular cylinder. The other one, if you want to add a vortex with a circulation gamma, you are going to simulate the flow of a circular cylinder with a spin. If it spins, what happens? It actually creates the drag. No, it creates the lift, depending on the direction. Okay, so that's something we are going to take a look at it. So this is your like basically something you want to know. So this is project 2A. This is project 2B. Okay. So stay tuned. Everything is purely math. So first of all, if you don't understand your math, it's impossible to do project 2A, 2B, period. Right? But if you know math, it takes 10 minutes to code. That's my impression. Okay? If you don't know math, it's impossible. If you know math, that's a piece of cake. Go ahead.
What if we know the math, but we don't know how to code?
That's a different issue because this is not MATLAB class. So, by the way, if you want access to my MATLAB homepage, you can. You know how to access to MATLAB homepage? Well, I'm teaching EGR, so just go there. That's it. Just actually have all the videos,
We only have
course
to link
material.
to.
Yeah, we don't have
Yeah,
access
see
to
it.
that.
Okay.
Like when you open it, it takes you straight to aerodynamics.
Yeah.
Too
You
bad.
don't have your actual.
Go there. So go one more step. This is my homepage.
Okay.
Then you can even access to FlyMac.
Yay.
I don't care.
Okay.
Go ahead, use it. As long as you are Embry-Riddle students, I have no problem. But if non-Embry-Riddle students using it, it's going to be lawsuit. Okay. It's a copyright invasion. Anyways, because it's copyrighted. But you can use it as long as you are a student of this school. I hope you continue to be. Actually, you graduate someday. Okay? So use it. EGR if you want to. But I'm not going to help you. You have to do your project. So let's take a look at uniform flow. Uniform flow. So this is the uniform flow. So somebody in the past actually solved the process equation in terms of phi and psi. Those are the solutions already. Okay, so we are going to put our eyes probably more on stream function. So uniform flow can be expressed in terms of velocity potential or stream function either way. We are going to probably use stream function as long as this is a 2D flow field. So this is a 2D xy plane or r theta plane. So one is in Cartesian, one of them is polar coordinate. Okay. So one thing you have to understand is in your project, you have to always go back and forth transformation coordinate from Cartesian to polar, polar to Cartesian. You have to do that all the time. MATLAB can easily do that, right? Of course. So this is the solution called uniform flow. So this is one of the solutions of the Laplace's equation. This is a solution of Laplace's. Called uniform flow solution. Okay, so we are going to pick up psi. You can pick up phi if you want to. However, you can quickly construct the 2D velocity field out of psi or out of phi. So if you take the partial derivative of psi with respect to y, that is velocity x direction component u. Okay, if it's 2D Cartesian, velocity is ui plus vj. Or in 2D polar, this is going to be Vr Er plus E theta, right? So velocity field can easily be given. So taking negative d psi dx is going to give you, this is going to be b. If it's polar coordinate, you can take 1 over r d psi d theta, which is b infinity cosine theta. B theta is minus d psi dr, which is negative b infinity sine theta. Those are velocity field. You can quickly get it. And then, of course, if this is MATLAB, you can quickly draw streamlines, right? Uniform flow, streamlines. Of course, you can do that. So this is going to be different. So if you draw a streamline in a uniform flow, this is a streamline. You can draw any number of lines, okay, by setting psi equal to some kind of constant value. Okay. Okay, so far. This is the starting point. So next thing is, let's just introduce you source and sink. So this is the second elementary flow solution of the Laplace's equation, source and sink, like I said. So we are going to probably focus more on psi, stream function. So this is solution of the Laplace's equation. This is a solution of the Laplace's equation called source and sink. Source is positive, sink is negative. Okay. Now this kind of flow field, it's probably easier and more convenient to employ polar coordinate system rather than Cartesian. Of course, flow field is always velocity only in radial direction. Tangential direction velocity is 0. Okay. Velocity is always radial direction, either outward or inward. This is called source. This is sink. Okay. Velocity is magnetic. So this is lambda.
Yeah, that's fine.
Okay. Okay. So lambda over 2 pi r, that's the velocity Vr. How do you get that, by the way? No, of course, same thing. You're going to get the velocity field over 1 over r d psi d theta. So if you do 1 over r d psi d theta, you're going to get the r. Okay, so this psi is lambda over 2 pi theta. Okay, So this is what 1 over r d theta of psi is lambda over 2 pi theta. So if you do this partial derivative easily, this is going to be lambda over 2 pi r, isn't it? Okay. Okay. So you can quickly get velocity field. This is a velocity, very simple. Velocity is only in radial direction component. Okay. And then obviously velocity in tangential direction component is 0. There's no velocity component in tangential direction. This is called source and sink. And then important thing is right here and right here. Those are called mathematical singularity point. Let's be very careful. Mathematical singularity point. This location is exclusive from your analysis. That means right here, the location of source and sink itself, you cannot use it as a physical solution. This is only mathematical solution. Not quite frankly, you can apply as it is for physical phenomena. Because right here, it's a straight violation of continuity. Divergence is going to be either positive or negative. That is a violation of continuity. Do you remember that? What is continuity? Del dot B is 0. This is continuity. That's going to be violated right here and right here. Okay. So let's be careful. So we're not going to use this point and that point, point O, meaning for physical solution. It's only mathematical solution. Okay. Okay. So this is source and sink, magnitude lambda. Lambda is a volume flow rate in this case, because this is incompressible flow. If it's compressible flow field, it's going to be mass flow. Go ahead.
And because they're radial, then v theta is 0, correct?
I guess so. Yeah, that's right. You can say that. In other words, velocity is only in the direction of r. Yeah. Okay.
If it's not good for like a realistic idea, like what is it useful for?
Yeah, so we are going to carefully avoid not using this location for actual flow field analysis. That means, okay, we're going to find out. So
Okay.
Let me just go back to you a little bit later as we start using it. Any other question? I guess it's probably better to look at with application. So, okay, good. So next page is application. So first superposition. Since I covered uniform flow and then source, let's just superimpose those two to try to construct a flow field. So I'm going to open up my software, and then I'm going to go for new flow. And then I'm going to superimpose, okay, let's say free stream of magnitude, I don't know, magnitude 1. And then superimpose with source of magnitude 25, just a guess, but here, this is point O, coordinate origin. So now I superimpose the uniform flow and then source of magnitude 25. Let's just start drawing streamlines. So what kind of streamline you can draw? 25 is too big, maybe. But anyways, you create a flow field like this. Okay? Flow field just like this. Looks like this is a stagnation point. Oh, you create a stagnation point right here over the body, and then flow is flowing over this kind of body. Okay, now, important thing is we are only interested in external flow field, just like this. Inside of this body, this is a singularity point. So this is going to simulate, suppose if you put this kind of body placed in the uniform flow incoming, what kind of flow field you can expect? So those are the areas that we are interested in. Inside of the body, I don't care, because that's not useful information. This is singularity point. Okay, so that's what we do. So this is the location of the source. So source is going to repulsive against incoming flow, sort of creating the body shape. This body is going to actually continue infinity. So this is simulated flow around leading edge of a semi-infinite body. It's called flow of a semi-Rankine body. Go ahead.
What would happen if you tried to put a streamline in between the stagnation point and the source?
Which is meaningless kind of thing, this kind of thing. So this is all trivial, something called trivial solution. In other words, this is a solution around mathematical singularity point, mathematically correct, but do you have any meaning in physics? No, that's the trivial solution, which is the flow field inside of the body is a trivial. So that means around here, this is called trivial solution. We are not interested. Mathematically correct, but we are engineers. We're not going to pick it up, consider as a real solution. So this actually creates, just a minute. So this actually creates simulated flow field of this kind of body. So this is a body of extending infinite distance, creating stagnation point right here. So this is the solid body in the flow field, semi-infinite body. So this is the simulated flow of a semi-infinite body this is called half-Rankine body. Question, go ahead.
I was just gonna ask, depending on the shape,
Yeah.
does the aerodynamic center of a wing kind of, is that?
Let's not talk about real thing. It's way too much jump. Let's just do step by step, step by step. It's dangerous because this one may not necessarily be representing something real. This is just a mathematical math. This is math.
Yeah, I just wanted to ask if it was somewhat similar to.
Somewhat, yes, but it's not quite a bit similar to it. We have to kind of,
Later on.
yeah. So this is like a very, very first step of what is the potential flow field analysis. We have more sophisticated methods coming up right now. Then at that point, we're going to talk about those things. Go ahead. Question? Yeah, go ahead.
I was just gonna ask, if you, like, take these sources and summate them over a camber line and have like a function that changes the intensity, is that how you get a point airflow?
That is same airfoil theory, which is actually in the, if you're interested, that's called same airfoil theory. You're not wrong, actually, there is an idea for it, but it cannot simulate the thickness though. It's only mean gamma. Any other question? So we are going to kind of step in a little bit more, one step at a time though. We are going to take care of the superposition next class, and then we're going to continue moving on. Okay. Let's stop here today. So we're going to see you back on Friday. Don't forget, we have a homework due.
Printer spit my thing out upside down, and I didn't bother to take it, so.
Oh, it's stapled on the wrong